Have you ever tried to pinpoint the exact moment a specific instrument played a fleeting note in a complex symphony, while also wanting to precisely identify the pitch of that note? It is a fascinating challenge, especially when we are trying to decipher the intricate electrical signals within the brain. The core reason time and frequency resolution present a trade-off in signal analysis is fundamentally rooted in the mathematical principles of the Fourier transform. Simply put, you cannot simultaneously know both the exact moment a frequency component occurs and its precise frequency with perfect accuracy. This phenomenon arises because frequency, by its very definition, describes a periodic event over a duration. To accurately determine a signal's frequency, you need to observe it for a sufficient period, allowing its repetitive nature to reveal itself. The Fourier transform, which is a cornerstone of breaking down signals into their constituent frequencies, inherently analyzes signals across a span of time. If you take a very short segment, or window, of a signal, you gain excellent precision about when something happened. However, this brevity means you have very little data to accurately resolve distinct frequencies, leading to a smearing or blurring of the frequency components. Conversely, if you observe the signal over a long window, you can identify frequencies with great precision, like telling individual musical notes in a sustained chord. But this comes at the cost of knowing exactly when those frequencies began or ended within that extended observation period. To navigate this inherent limitation, neuroscientists and engineers often choose their analysis window strategically based on their specific research question. If you are tracking rapid, transient neural events, like spike timings, you will opt for shorter time windows, accepting a broader estimate of frequencies present. However, if your goal is to precisely characterize the dominant oscillatory rhythms, like alpha or gamma waves, you will use longer windows, sacrificing some temporal localization for superior frequency clarity. Advanced techniques, such as wavelet transforms, offer a compromise by using variable window sizes, narrow for high frequencies and wide for low frequencies, but even these methods do not entirely escape the trade-off. This fundamental principle is sometimes referred to as the Gabor limit or the uncertainty principle of signal processing, which states that the product of the effective duration and the effective bandwidth of a signal must be greater than or equal to a constant. Another crucial aspect to consider is spectral leakage, which happens when a signal is not perfectly periodic within the chosen analysis window. This can cause energy from one frequency to appear at adjacent frequencies, and different windowing functions, such as Hamming or Hanning windows, are applied to mitigate this effect and improve the clarity of your frequency estimates. Understanding this time-frequency trade-off is absolutely essential for anyone processing brain signals, as it guides critical decisions in experimental design and data interpretation. By thoughtfully selecting your analysis parameters and understanding the compromises involved, you can extract the most meaningful insights from complex neural data, whether you are focusing on the precise timing of events or the subtle changes in brain rhythms.